Well, so far, everything we've been differentiating basically been polynomial functions. So the powers have all been positive whole numbers. Well, how do we differentiate things that are not cardinal numbers? So in other words, fractions and negative numbers. Let's have a look at that. So y equals 1 on x. First of all, let's deal with negative indices. So function x is 1 on x, so we're going to have to go back to first principles to see if we can create a formula. So function x is 1 on x. Function x plus h will be 1 on x plus h. We plug it into our formula. All right, let's tidy this up. We've got fractions on fractions. So we'll send the x and the x plus h to the bottom of the fraction. But then how have we changed it? The first fraction now needs x on the top because I've multiplied the denominator by x. The second fraction now needs x plus h on the top, but it's minus that, so it gets minus x minus h. And on the top of the fraction, excellent, we get h on top, which means we can now cancel the h's and come up with an answer. Now if we substitute in 0 for this one to find the limit, we'll get minus 1 on x times x, which is of course minus 1 on x squared. So to have a look at that closely, what does it mean? Well, hang on. If I used negative indices, I could have said function x is x to the negative 1. Now if I ignore the fact that all we've proven it for before was positive whole numbers, let's use the rule, see what happens. We would bring that power down, negative 1 comes to the front, we would lower the power by 1, negative 2, which is minus 1 on x squared. So effectively what we've just proven here is that we can still use the rule for negative indices as well. So terrific, we don't need any new rule. Well, let's have a look at fractional powers. Let's see if the same thing happens there. So function x will be the square root of x. Function x plus h, square root of x plus h. Plug it into our formula. Well, what can we do with this? I guess what I'm going to do is the opposite to what we usually do. I'm going to rationalise the numerator rather than rationalise the denominator. But it still means multiplying it by the conjugate. So the top of the fraction becomes x plus h minus x, which is great because that just leaves me with h on top, which will now cancel with the h on the bottom of the fraction. And let's see what we've got. So if I can, yes, I can now substitute in, when I cancel those h's, if I substitute in h as 0 to that one, I'll get 1 on root x plus root x. So that's 1 on 2 root x. Again, let's have a look at what would happen if I use the normal rule that we have anyway. So function x would be x to the power of a half. Put that power to the front, I'd get a half, subtract 1 from the power, negative a half. Well, x to the negative half means the square root of x is on the bottom. So yes, we do get the same answer. So what that means is that rule we originally came up with, we can use for any power we like. Doesn't have to be a positive whole number. It can be anything. Let's look at one. So if we have y equals 3x plus 1 on x squared, well, before we do it then, we'll put everything into index form, and then we can use our rule. So the 1 on x squared can become x to the minus 2. Now we'll differentiate it. 3x becomes 3. Be very careful with your negative numbers. So the negative 2 comes to the front, but remember you're subtracting 1 from the power. Don't make the mistake of making it negative 1 because you're used to going from 2 to 1. You're subtracting 1 from the power. So the power goes to negative 3. That is an answer. I always like to leave my answer in the format they gave me the question. So they didn't use negative indices in the question, so I'll just write it as 3 minus 2 on x cubed. Do you need to do that? I guess it all depends, what are you going to do with the derivative? Now, if you're going to substitute numbers into it, is it easier to substitute into 2 on x cubed, or is it easier to substitute into x to the negative 3? Well, and that's your decision to make, how you'd prefer to do it. So there'll be some situations where the second line of the derivative there would be the useful one, and sometimes the first line would be good enough for an answer. All right, let's have a look at example 2. X squared root x. I want to put that into index form. So I've got x squared times x to the half, add the powers, 2.5, but we write them as improper fractions. 5 on 2, isn't it? So yes. So we've got x to the 5 on 2. Bring the power down, subtract 1 from 5 on 2, we get 3 on 2. Again, do I leave it like that? Well, I'm going to put it in the format of the question. X to the 3 on 2. 3 on 2 is 1.5, so it becomes x root x. So 5 on 2, x root x. So example number 3. This is where it's now good because how would I have done this before? I couldn't have expanded out 5x plus 4 to the power of negative 2. So how would I have done it? So let's put it into index form. Guess what we get to use now? Anarchy. All right? Bring down the power. So bring down the power. It becomes minus 4. Lower the power. Minus 2 becomes minus 3. Diff the inside. Differentiate 5x plus 4. We get 5. Tidy that up. Again, that's probably good enough for an answer. That's what a mere mortal would leave the answer as. But us super mathematicians will match the question and we'll end up with minus 20 on 5x plus 4 cubed. Part 4, square root of x squared minus 3. We put it into index form, power of a half, but once again I'm now going to use anarchy. Bring down the power, half. Lower the power, becomes minus a half. Diff the inside, 2x. Let's tidy that up. So I have x times x squared minus 3 to the minus half. Mere mortal answer. Super mathematician answer. So the x squared minus 3 to the power of minus half goes to the bottom of the fraction and becomes the square root of x squared minus 3. Okay, that'll do us for today.